Thank you, Alex, and hello, everyone. It's nice to make your acquaintance over the Ethernet. So, or the ether. So, I'm going to talk about building rocky worlds, and it's kind of a grandiose title, but I will keep it short. So, don't worry. I'm not going to cover everything. I'm just going to cover a few aspects of building rocky worlds. Before I start, I just wanted to show you the other side of what I do. So, the image in front of you is from La Palma 2021, the eruption of La Palma. And I did my PhD on La Palma in the early 2000s. So it was really a pleasure for me to actually witness it erupting. And so we've been working very heavily on that eruption and also eruptions from Iceland and Mauna Loa in the recent couple of years. So that's kind of one other aspect of what I do so that you're familiar with my work. So what I want to talk about today, though, is building rocky worlds and the implications it has for exoplanetary systems. You can see a short abstract in the top left, and it points out that we have a solar system with rocky inner planets, with some with relatively small cores, others dominantly being airless bodies like Mercury, and some of the bodies, including, of course, our own Earth, being having water oceans, being oxygen-rich atmospheres in the case of the Earth, having abundant life. And so what I want to talk about is some of the implications our isolated calibration point has, which is our solar system, for understanding exoplanetary systems. And I'm going to focus particularly on the early stage melting of planetary bodies. If any of you have burning questions, I know Alex said put them in the chat, but if you have burning questions and they need to be answered, just interrupt me. I have no problem with you doing that. Okay, so let's move on. I just want to point out that there's a brilliant website on the NASA website. It's exoplanets.nasa.gov. And it shows you the currently known and confirmed exoplanets, the number of candidates, and the number of planetary systems. And it's probably no surprise to all of you that these are just going up. They're almost growing exponentially. I'll show you the actual plot in a second. And we know that there's over 5,000 confirmed exoplanets. There's 10,000 candidates, and there's 4,000 planetary systems. And it always blows my mind that before 1995, we genuinely thought that the Earth and the planets around our star might be unique. That is clearly not the case. This is just one example on the website of a world that's in lockstep with its star. So it's in gravitational torque with its star. So it's always facing in one direction. And it's molten on one side, one hemisphere, and it's solid on the other, they think. This shows you the cumulative detections per year of known and confirmed exoplanets. And you can see it's nearly an exponential rise, especially in the early to mid 2010s. It's slowed down a bit, and that's because of the Keck mission to look at these planets being decommissioned. But what we're going to see is an explosion again as new remotely sensed telescopic missions are flown in space to look for these tiny, tiny exoplanets, at least as we see them from the distance of the Earth. The cumulative detections per year, what you'll notice is that the first confirmed detection, was around 1995. That was the Nobel Prize winning detection. And since that time, you'll notice that there's a massive number of detections by transits, and I'm going to explain what that means. And there's a very few detections by direct imaging. That's imaging on this diagram. Now, transit photometry, which is the most common method, is where you basically see a dimming of the star as a planet goes around it. This is important to note because you have to see the planet go around the star multiple times to get a confirmation. So that by definition, according to Kepler's laws, you have to be pretty close to the star. And so these tend to be planets that are very close to their star and are not Earth-like at all. There are these make up about 75%, by the way, of all planetary detections. There are other methods that you can see shown here. This is taken from the NASA website, the ESA website, I should say. Very nice way of showing the detections. And what you'll notice is that around 1% of all detections so far are direct imaging. That's where light that's being reflected off the planet is being observed directly on Earth, or conversely in flying telescopic missions like Kepler. And these are really important because the composition, the spectra of the light that's coming off these planets tells you something about the composition of the planet itself. The Kepler mission that was flown in space was able to see planetary masses smaller than the Earth, and as big as 10,000 times terrestrial mass. The problem was with the Kepler mission is it could only see orbital distances about 1 astronomical unit from its star. That's about 90 million miles or 150 million kilometers. Now that's good, but what you'll notice is shown in this diagram of orbital distance versus planetary mass, that the Kepler discoveries are normally slightly larger than Earth-sized planets, and they also tend to be close into the star, more sort of Mercury distance or even closer to their star. The new missions, including, for example, the W1 mission and the Nancy Grace Roman mission, will be able to see things that are much more Earth-like. So we're going to see more of these direct detections and more solar system-like bodies that we're going to be able to look at the geochemistry of. And this is why, understanding our own calibration point in space, which is our solar system, is so critical. There are other ways to detect compositions of exoplanets. So you can detect them directly. You can look at the composition of the star around which they form. In our own solar system, as I'll show you, the bulk composition of the solar system is defined by more or less the photosphere of the sun. And that's very similar to the earliest in composition, to the earliest formed condensates, which are chondrite meteorites. So if you take that view, you can also use the star itself to understand something about the composition of the exoplanets that might form around it. Another method is to use polluted white dwarfs. So these are small stars into which the planets around them have already fallen. And so the stars are, if you will, a bit like a plasma instrument. They destroy and ionize all of the elements in these falling planets and enable you to measure directly the compositions of the planets that have died. So these are deceased planets, if you will. And what you'll notice in the bottom left-hand side of this slide is a mass fraction, so the total mass fraction of major elements, in this case, oxygen, magnesium, silicon, iron, carbon, and other elements, and these various different polluted white dwarfs. And also shown on here is the composition of Halley's Comet and the Earth. And you'll notice that many of these polluted white dwarfs have had planets fall into them with uncannily similar compositions to our own Earth. Was there a question? I heard some noise there. No question? Okay. Now, what I'm going to say today is very specific, but there was this really nice Elements magazine a series of articles that came out about geoscience and the solar system and exoplanetary studies. And I particularly like this quote by Paterka, Dawn, Hinkle, and Unterborn, which says the disciplines of geology and astronomy have existed at a considerable remove for greater than 300 years. The discovery of rocky exoplanets during the last 2 decades, however, requires the closing of that distance. Knowledge and methods in one discipline can affect hypotheses in the other. The limitations in each field drive innovation in the other. No better example is the interpretation of rocky exoplanet compositions. So with that in mind, and with this background of exoplanets, I now want to sort of go into some of the aspects of building rocky planets. So specifically talking about planetary worlds that don't have large gas atmospheres or are gas giants like Jupiter and Saturn, for example, and particularly focusing on planets where you might foreseeably see evidence for life. Now, where you find exoplanets that are conducive to life depends on, the Goldilocks rule. Not too hot, not too cold, just right. And that really depends on the size of the star, the evolution of the star, the age of the star. These are just some images to show you examples of where habitable zones might be around stars. And it can vary from Earth-like conditions around a G-type star like the Sun to, much greater astronomical distances in larger stars to even distances very close to small stars. It also depends on the evolution of the star. As we hopefully know, large stars die young. Very, very big stars are not conducive to habitable conditions. Whereas Earth-like solar systems, where you have a G-type star, a smaller star, tend to be more conducive. So these are the places that we want to look, and this is exactly where these new telescopes are going to be looking. It's really interesting to note that stars that we have observed with planets around them tend to have higher metallicity than our own solar system. Now, when I use the term metallicity here, I'm talking about astronomical metallicity. That means everything greater than hydrogen in terms of its mass, atomic mass. So what you can see in the bottom left-hand panel is a classic diagram from Fisher and Valentini. This is a classic paper in astronomy where they show the iron-hydrogen ratio of stars that are known to have planets around them. Earth would be at 0.00 on this diagram. And what you'll notice is that the great majority of stars with planets around them are actually of higher metallicity than our own planet. Shown on the right-hand side is atomic number versus metallicity. So that's X over H on this diagram. And our own star and our own planets would fall at 0.0 on this diagram. Again, you'll notice that planets that host stars with planets around them, they've said that the wrong way around, are more metal rich. They have higher metallicity. So this raises another question, which is when we're thinking about our calibration point, just how similar is it to the stars and planets that we're observing? For example, would a planet that had formed at much higher metallicity look that's of the same broad size as our own Earth and the same distance from its star really look the same? I want to focus on a very particular aspect of that, which is the very important major element, aluminium or aluminum. I'm British, so if I say it either way, please forgive me. Alumina is a very important element because early in the evolution of our own solar system, what we now know is that there was a significant fraction of the radioactive isotope or nuclide of alumina, aluminium-26.
It's the department seminar. Wait,
oh, hello. Sorry, someone was talking there. Now, aluminium-26 has a half-life of 720,000 years. So it's completely decayed within about 5 million years of the formation of our solar system. Now, I mentioned that many of these exoplanetary systems have a higher metallicity than our own solar system. So it's fair to say that many of them may have had an even higher proportion or fraction of alumina-26 during their formation. This is thought to be a really important element because it decays very rapidly, is a major element, and so should have been present within rocky bodies early in the formation of our own solar system, and for that matter, in every other solar system around a newly forming star. There was this very interesting paper in Nature Astronomy in 2019 called A Water Budget Dichotomy for Rocky Protoplanets from Aluminium-26 Heating. In that paper, they proposed that essentially what will happen is if you have a solar system that is rich in aluminium-26, like our own, you will end up with broadly dry planets, as shown on the right-hand side of this diagram. If, on the other hand, you are forming from around a planetary system around a star that doesn't have such a high aluminium-26 quantities, then you would end up with ocean worlds. Now, this paper has been cited significantly and is widely held to be one of the examples of how we might interpret exoplanetary systems. What I wanted to do in this talk is focus particularly on aluminium-26 in order to understand what our own isolated calibration point, which is our solar system, might tell us about whether this particular hypothesis is correct or not. Just to give you a sense of the scale of our isolated calibration point, this is a diagram that I made shown in C at the bottom of the region of the rocky inner planets. Shown on this diagram is something that you might not have been familiar with, but it's showing you Mercury, Venus, Earth and its moon, and Mars, and then outboard of Mars is the asteroid belt. And what it's showing you is the relative proportions of ensitite type, stony type, and other types of asteroid. It's just a way of portraying the asteroid belt. And if you then zoom out again, so you can see the gas giants, shown in B is the region of the solar system with the gas giants, and you can see the inner solar system from section C in there, and you can immediately see how small the rocky planets are in terms of our own solar system. And then what I've done in A is to zoom out again to beyond the heliopause and to the Oort cloud, just to show how small the calibration point is that we're dealing with. Now, it's important to note that so far as we know, all of the material that we have in meteorites comes from the region that's shown in C. It's possible that we have material from outside of that region, but it's kind of hard to prove that. We can certainly say with great confidence that most of the meteorites that we have come either from Mars, the moon, or from the main asteroid belt. So this is something to bear in mind when we talk about our calibration point. We know that our solar system is formed from a number of stellar sources. We know this from nucleosynthetic anomalies of isotopes in various chondrites and their parent bodies. That's shown in the top left-hand diagram here. So we know that our solar system comes from a mixture of Big Bang nucleosynthesis, cosmic ray processes to produce lithium, beryllium, and boron, for example, and from multiple stellar sources. I have shown here 3, and they're mixing, but it could be more. We don't know. Shown in the bottom left is Mendeleev's periodic table, shown in the modern way, but showing you the different distribution and sources for these various elements and their nuclides. And in the top right-hand panel is just showing you the composition of our solar system in log relative abundance over silicon versus atomic number. We know our solar system quite well. we don't know exoplanetary solar systems anywhere near as well. And that's why our solar system is so critical as a calibration point for future work in exoplanets. This is just really a reminder. We also know from our solar system that elements condense in a predictable sequence. So shown in the top right-hand portion of this slide is the pillars of creation, shown both from JWST and from the Hubble Space Telescope. And they're showing different images. One is infrared, one is spectral. But you can see this wonderful feature. It's very large. And, our solar system would look tiny in this image. And we know that planetary systems are probably forming around the nascent stars within this region as we speak. So presumably in those systems, depending on the metallicity, you'll have a very similar condensation sequence to that shown in the bottom left-hand panel, which is temperature versus fraction condensed. And what I want to draw your attention to is the highly refractory early condensates. In particular, these contain the oxide, aluminium oxide. So that's where alumina 26 will reside during the condensation of these early solar systems, as it did in our own. We also know that there's some mechanism by which you form the planets. And shown in the bottom right-hand panel are three such mechanisms. I won't go into the details of these, but it's kind of hard actually to go from early condensates to actual planetesimal sized bodies. So I'm talking bodies kilometers in scale. And so these three different ideas of core accretion, streaming instability, and pebble accretion, these are just three different models to explain potentially how you go from these early condensates to planetesimal sized bodies. But we know that they happen because not just our own solar system where we have planets, but there's a whole bunch of exoplanetary solar systems now. So this seems to be a ubiquitous process around stars. Let's talk about aluminium 26 because it's really important to understand just how important this is as a heat source. In our own solar system, the alumina content of the solar system is around 8,400 parts per million. That's about 0.84%. Of that, we know that the initial aluminium 26 to aluminium 27 ratio is about 0.0005. That equates to a total alumina 26 content of around half a part per million. Now, if you calculate how much energy that produces, it's about 1.8 million electron volts per decay. Now, you can reconfigure that into how rapidly and effectively it would melt a planet or planetesimal. Now, the best way to do this is to take a small planetesimal because likelihood is that the earliest bodies in our solar system were small. They were small and then they were built big. It's very unlikely that you build planetesimals big in the first instance. And what you can calculate is the energy released from aluminium 26 decay results in as shown on this right-hand image. So shown at the bottom here, so this should say millions of years, so going from 0 to 8 million years, and the temperature in Kelvin going up to 2000 Kelvin. Shown here is this red line. This is showing you the amount of heating that would happen from radiogenic decay of alumina 26. Also shown on here, I put the temperature at which you would get initial iron nickel sulfide melts from a chondrite. Remember, we think chondrites are the things that are the bulk composition of the rocky inner planets and of our own star. And also what I've shown is the initial sodium, alumina, and silicon-rich melts that would be produced. And what you can see is that within about less than 1 million years, provided there's sufficient aluminium 26 around, you would be able to easily melt to silicate melting on any moderately sized planetary body. This is well known, but it just shows you how effective it is. Also, I've shown on this same plot the fraction of remaining aluminium-26, so you can see how rapidly it decays. But in the very top panel, I have shown at the same scale, so these are now in 4568 to 4560 million years before present. We think that the solar system formed around 4568 million years ago, showing you different solar system materials and their times of formation. And it's interesting to note, yes, you have chondrules on here. These are materials that are within chondrites. But what I want to draw your attention to is the magmatic iron meteorites, the non-magmatic ions, angerites, and Vesta. These are all differentiated bodies. And it's highly likely that these differentiated in no small part because of the decay of aluminium-26. So we have really strong evidence that aluminium-26 was a major player in the melting of planets. That's exactly what Lichtenberg said in their paper in Nature Astronomy, and that's why they said that exoplanetary systems would also suffer a similar fate. Now, it turns out our own solar system has some really interesting rocks coming from it. Well, there's many different types of rocks. These happen to be some of my favorites. These are the asteroidal andesites. So these are andesitic composition rocks, the Graves Nunatax andesites from the region of Antarctica close to the South Pole, shown here on the top right. So it's the GRAs just on that diagram. They're the first andesitic materials from an asteroidal body. And you can see that they're these blocky looking meteorites with a fusion crust. You can see the dark fusion crust. And they're just a really interesting suite of rocks. And I'm going to show you they're really powerful for testing these and other rocks, are really powerful for testing some of the hypotheses regarding aluminium-26 decay. Because it's not just them. We now know that there's another whole group of andesitic achondrite meteorites formed very early in the solar system, one of which is Erdchech 002. This is another fantastic looking meteorite. You can see some images just shown here. These are some images from various, actually, these are from our lab. You can see a nice slice through a section of Erdchech in the left-hand panel. And you can see a backscatter electron image of Erdchech, or a piece of it, in the right-hand panel. Multiple asteroidal andesites now. And these are really useful for examining what happens during really early stages of differentiation in planets, because these are the sodium, aluminum, silica-rich melts that come out of those primary melting processes of planetesimals. You'll notice that Erdchech formed within 1.5 to 2 million years of CAIs. These are calcium aluminum inclusions. These are the earliest refractory condensates of our solar system. Now, these andesites, these asteroidal andesites, they're not like andesites on Earth. Yes, you can plot them on a total alkali versus silica plot, like the one in the top right-hand panel. That's silica versus sodium and potassium, very typical way that we would show stuff for the Earth. In fact, on that plot, you can see the continental crust, shown here as CC. And you'll see that the continental crust of our planet has an andesitic composition. Erdchech lies right in that region. So do the GRA meteorites. They're more like andesites to basaltic tracking andesites, or BTA on this diagram. And then I've shown a number of other andesitic to closely affiliated meteorites, just to show that they really do kind of cover that spectrum of andesitic compositions. They're sodium aluminum rich melts. They're early formed. They come from bodies that are still sufficiently warm to engender melting. Just on the left-hand diagram is that same figure I showed you before, just to remind you how effective aluminium-26 decay is at engendering melting potentially in these bodies. Now, yes, they produce andesitic compositions that are reminiscent of Earth's continental crust, but in terms of their trace element compositions, they look nothing like the Earth's terrestrial continental crust. The Earth's terrestrial continental crust is formed over time by subduction processes primarily. And so on a diagram of rare earth elements versus, say, rock over sea chondrite, so that's shown on the bottom right-hand panel, you can see that the average terrestrial andesitic continental crust has a very steep, light rare earth element enriched composition. These asteroidal andesites are shown just beneath it, and you can see that they have broadly flat chondrite-like patterns, very similar to what you would expect for primary melts from an asteroidal parent body. So there's many ways that you can produce andesites. That's just showing you on the left-hand panel. I've shown now an orange bar just to show you when these things were forming. Right around the time that aluminium-26 would have engendered extraneous heating to melt these bodies. We can do all kinds of modeling, and I'm not going to express too much about these. You're welcome to go and read about our models because they're somewhat complicated, but you can use rare earth element modeling as shown in the left-hand panels, and you can estimate that these asteroidal andesites form from around 13 to 30% partial melting of a chondritic body. There was this wonderful paper by Collinet and Grove in 2020, where they were able, this is a major step forward because what they were able to do is take chondritic type compositions and not lose the sodium from the experiments that they were heating. That was important because what that showed is that you can produce these asteroidal andesite-like compositions just from partial melting of specific types of chondrite. So this is a very important paper, and it confirms what we suspected of around 13 to 30% partial melting to produce things like the GRA meteorites. What's really remarkable about these andesites, they're not all coming from one asteroid. They're coming from multiple asteroids. We know this from oxygen isotopes as well as chromium and titanium isotopes. And I'm just showing you oxygen here. So on the left-hand panels are a typical way that we would express oxygen isotopes. So we're showing the delta 17O or delta O18 of these bodies. So this is the 18-16 ratio that you measure of your sample over the 18-16 ratio of a standard, normally standard mean ocean water, -1 times 1,000. And so that's what that is showing you. And you can see that there's all kinds of compositions on this diagram. I just want you to realize that the terrestrial fractionation line, or TFL here, is where all things on Earth plot, except for some atmospheric compositions. And you'll also notice these CR, CH, CB, CV, CM. These are carbonaceous chondrites, and you can see how distinct they are from the Earth. So this is a really good way of distinguishing parent bodies. Shown in the bottom panel, B, is this unusual thing, this cap delta O17. This is the deviation from that terrestrial fractionation line. And so you can see that on Earth, all things would lie along the TFL, but these parent bodies of these andesites do not. In fact, shown in the right-hand panel is a plot of cap delta oxygen 17 versus the iron manganese ratio. And you can see that there's now shown here are multiple andesite type compositions, NWA 11575, doesn't matter which, it's a Northwest African meteorite, GRA, Erdchech, and then some others, Alma A and NWA 11119. And you can see that they're coming from distinct sources with distinct cap delta O17. That means they're coming from at least 4 parent bodies, probably more than 5. So this is a ubiquitous process. This is not an anomaly in our solar system. This gives us confidence that if we're looking at these processes and how these rocks are forming, they can tell us something really important about the behavior of aluminium-26 and aluminium in general during planetary differentiation. So this is a widespread process. I like this diagram because it's Yosemite versus Ida and Dactyl. These are really cool asteroids that are in lockstep with, they're orbiting one another. Well, the smaller one is really orbiting the larger one, but just, I don't know if Ida and Dactyl are andesitic in composition. It would be cool if they were, but I just like this diagram. But the point is that there's widespread aluminium sodium-rich partial melting of small bodies in the early solar system. This gives us a way of testing some of those hypotheses that maybe aluminium-rich solar systems will lead to dry, rocky planets, and aluminium-poor ones will lead to water-rich planets, and I'll show you why. Before we get to that point, I need to point out some other stuff that we're going to show you. So in my toolbox, what I like to study are the highly siderophile elements. These are a great set of elements. There's 8 of them. 2 of them, rhodium and gold, are monoisotopic. So they're very hard to measure without using specific lab techniques. The way that we get very highly precise concentration data for these elements is we use a method called isotope dilution. And that relies on having more than one stable isotope of these elements. So we tend to focus on the 6 that are not underlined here, things like osmium and palladium. Now, what's amazing about these elements, and Goldschmidt knew this a long time ago, is that if you take something like a chondrite, shown in this diagram here, this is a lovely chondrite with a CAI right there. If you take that chondrite and you melt it, what you end up with is you end up segregating all of the metallic iron into the core because it's very dense. It'll go into the center, the gravitational center of any parent body. Now, these are called highly siderophile elements for a reason. They like to go into metal. So what happens is you leave the silicate mantles of planets virtually devoid of highly siderophile elements. Now, you might be wondering, well, how does this relate to aluminium-26? We've measured these asteroidal andesites. And what's shown in the top right-hand panel are the asteroidal andesites that we measured for these highly siderophile elements. So those highly siderophile elements are shown in relative order of incompatibility, going from the most incompatible on the left to the most compatible on the right. In general, they're really compatible elements, but this is the way we show it. This is sample over CI chondrites. So CI chondrites, or chondrites in general, would lie within about 30% of the 1 line on this diagram. And what you can see is that the GRA meteorites, my favorite meteorites, are pretty close to chondritic compositions. However, Erdchech and these new asteroidal andesites that we've measured are not. They are strongly fractionated, and this suggests that they had formed cores even before they formed these asteroidal andesite compositions. Now, that's very interesting. That suggests that some of these early planetesimals were forming cores very, very rapidly. This is completely consistent with what we know about iron meteorites. We know that iron meteorites come from the cores of planetesimals, and they form extremely early. So this is all very nicely coming together. There's similar degrees of partial melting, and shown in the top left are some of the interpretations. What I want you to focus on is the bottom left, my idealized diagram for how you might envisage these things forming. So in the case of the GRA meteorites, on the leftmost portion, the gray view of an asteroid, these are probably high iron, magnesium, HSE-rich melts coming from partially melted asteroid. That asteroid probably has formed some form of nascent core, but it hasn't completely melted. On the other hand, Erdchech and these other asteroidal andesites that we're discovering coming from different parent bodies, right, based on their oxygen. They're not the same parent body. These are coming from asteroids with fully formed cores. So not only do we have evidence that these are telling us about processes in the solar system for the differentiation of aluminium, but they're telling us they're coming from asteroids that have seen quite distinct evolutionary histories. Now, there's supporting evidence in the meteorite record to show that this is a very common process. I'm just showing you some nice images of various types of meteorite in the left-hand photographs. So some of you might recognize an A and B, that's Chelyabinsk that fell in 2013. C is a lodronite, and then F and G, those actually, F is diogenite, G and H, those are eucrites. These are different types of meteorites. And in E, that's a brachyonite. These meteorites have all shown this progressive change from partially differentiated or undifferentiated bodies like those represented by winnerites that are very similar in composition to chondrites, where they're rich in metal. And then you see this kind of removal of metal to things like brackionite-like chondrites, all the way to fully differentiated bodies like those that form the eucrites. That's probably the asteroid Vesta. So we're not looking at a microcosm here. We're looking at really important large-scale processes. When you're trying to use a calibration point to answer a question, you need to demonstrate that that is the case. Now, why would the asteroidal andesites be so important? It's shown in the top right-hand panel. If you have a body that is rich in aluminium-26, and you then melt that body, and you form sodium aluminium silicate rich melts, the first thing that body does is it self-eviscerates. It removes all of the heat-producing aluminium-26 from its interior. This is really interesting because one of the arguments by Lichtenberg in their paper was that aluminium-26 rich bodies would melt and become volatile poor. Actually, what we observe is not that at all. We see that these asteroidal andesites are quite volatile rich. So this idea is then that you could produce aluminium-rich melts from these asteroids that then actually eviscerate the body of the radiogenic heat-producing element aluminium-26 and essentially freeze it. This is very important because these bodies are ultimately going to be the feedstocks for the larger planets that form. So if we go back to Lichtenberg's hypothesis, he argued that volatiles were strongly affected by aluminium-26. Now, I'm not going to show you the very complicated volatile plots, but I can reassure you that GRA and all of these other asteroidal chondrites are not particularly volatile poor. So furthermore, when you eviscerate a planetary body of these aluminium-bearing melts, you retain a significant fraction of volatiles. So it's not necessarily true that if you're from a higher metallicity, higher aluminium-26 source, that you're going to end up with necessarily dry bodies. That's the first point to make. We kind of know this. We know this because we've known for a long time that if you look at our solar system, the inner portion of our solar system is, broadly speaking, rocky and kind of dry. We also know that if you look at the outer solar system, we have the gas giants, which are clearly not. They are, they have very similar, most of them, similar hydrogen-helium ratios to our sun. And then within the main belt, the main asteroid belt, we see this difference in composition of asteroids from ones going closer to Mars on this diagram that are Ensitite or E-type and stony, to asteroids that are more volatile rich, like the carbonaceous or C-type asteroids and the D and P type asteroids. So we've known for a while that actually it's not necessarily true that if you have a solar system that's alumina rich, that it will be dry. We know that there can be a mode, and actually it seems that the strongest control seems to be distance from the star itself. Just to give you a sense, I mean, if you know, we're very easily able by remote sensing these days to measure the potassium uranium or potassium thorium ratios of planetary bodies, because we can use gamma ray detectors to detect the decays of these elements in these bodies. And so this is just showing you a potassium uranium ratio versus distance from the sun of various bodies, including Mercury, Venus, Earth and the Moon, Mars, and I've also shown on here Vesta, which is in the main asteroid belt. And you can see that there's not a strong coherence here. You can see that broadly speaking, the larger planetary bodies, more potassium rich, have a higher potassium uranium ratio than, say, the Moon or Vesta. The modes, actually, I'm just going to show you one diagram before that because I've got them in the wrong order. The other thing we know is that parent body size really matters. Parent body size is critical, and shown on this diagram in A, I want to draw your attention to A, is log surface gravity versus the potassium isotopic composition of rocks from different planetary bodies. Shown is Earth, Mars, Moon, and the asteroid for Vesta, or the likely source of eucrite meteorites. And what you can see is that there's a very strong inverse correlation between log surface gravity and potassium isotopes. And what we proposed in this paper is that parent body size, anything smaller than Mars, that fully differentiates, is going to be largely volatile poor, and anything bigger than Mars is likely to retain its volatiles quite well. So just going back to this diagram, where do you get water-rich bodies coming? Why are some bodies more water-rich than others? Now, one idea is that it's from late accretion. This is the idea that you had main accretion, where you may have had dry planetary feedstocks, or you may have lost volatiles during the accretion of the planet itself, followed by late accretion, which is this delivery of a small tail of water-rich material onto the planet. Also shown on this diagram is a secondary clearing event, which may be a moon-like clearing event. The point here is the Lichtenberg idea about, exoplanets may or may not form wet or dry is much more complicated than that, far more complicated than that. And our calibration point tells us this. Just to show you how complex it can be, when I was taking planetary classes, I was told that planets form from chondritic meteorites. Well, I think that's nonsense. Planets form from a mixture of partially to fully differentiated chondritic bodies. It seems very obvious that that's the case because when you form planetary bodies, you have to build to these larger bodies, and they don't just wait for differentiation to take place. They still have aluminium-26, they still have heat from accretion, and they still have heat from core formation as they're forming. So it's likely that the mixture of bodies that form planets like our own, if you will, the thing on the right hand, the slice on the right-hand side, is a mixture of both fully differentiated bodies, like the one with the silicate magma ocean and metal core, bodies with perhaps felsic crust like GRA and metal sulfide segregation, and chondritic materials. And we can kind of see that in our solar system if we just look at a basic plot of things like core size versus total radius. So this is a diagram. And the bottom diagram shows you the hypothetical size of a core of an H chondrite. This is a high iron chondrite, ordinary chondrite. And what it would look like if you were to take that chondrite, melt it, and form your own planet from it. You would end up with a planet that had a core size about half the size of the total radius of the parent body. What we see in our own solar system is that things like Venus and things like Mars have broadly chondritic core sizes. We know that the Earth has a slightly anomalously large core size. The Moon has a subchondritic core size, and Mercury has a superchondritic core size. Now, there's been many hypotheses as to how you do this, but one is actually that if you form these planets from variably differentiated bodies, you can produce variable core sizes. So what are the implications of this? The implications are several. So the first one is that the initial inventory of elements into solar systems is really important. Metallicity matters. Aluminium, just because you have more alumina-26, does not necessarily hold true that you're going to have ubiquitously dry planetary bodies. Our solar system tells us this, and we have strong evidence to show that. The evolution of the feedstocks is probably more important for what kind of planetary outcome you have, what you form your planets from, how quickly you form them. Planetary accretion and differentiation mechanisms are likely to be broadly similar from what we understand, but they're going to be important as well. And that late accretion is going to be critical to whether we think exoplanets might have the potential for life or not. And the thing that I didn't touch on is that the later evolutionary history, such as tidal locking, things that we don't really think about for our own planet, are also critical. The diagram on the left just shows you various hypotheses and ideas of exoplanet compositions, images from NASA. These are based on star composition or direct imaging. And so you can see that we're beginning to get really quite complex. In the case of the bottom one for Kepler 102, they've done mineral physics to determine what kind of minerals you might expect to see in the silicate mantle. From a chemical standpoint, our solar system calibration point is important. It shows us that the initial inventory of elements is critical, that feedstocks are essential, and that processes are complex, and they can be revealed through the studies of meteorites. And so with this, I want to end by saying, first, thank you for your attention. Second, I want you to think, as you're looking at these exoplanets, about what meteorites can help us understand about what those exoplanets might look like. And the image on the left, I'm afraid, is just an image taken from one of these exoplanetary papers. And you can see the complexity of some of the models that are being produced. And many of these models don't consider what we understand from meteorites. So with that, I'll thank you very much for your attention and leave you with a nice picture of collecting meteorites in Antarctica.